of the 3-coordinate defect plays a very, very important role. I am not going to talk about the definition of a hydrogen bond that has been written today. Okay. So snapshots of supercooled liquid, this is a high density and low density region. This reddish brown is the high density. So at high temperature, I already showed you the high density region is percolated. Okay. Or is percolated. As I go to lower, this is where the first time the percolation of the low density amorphous ice takes place. 180 Kelvin, you can see very few pockets of high density, almost defects. Everything has become low density. This is not ice. This is what is like amorphous ice. Very small high density patches in percolated low density water, which are with defect. This is not ice. So these transitions, what we call multiple transfiguration, plays a very important role. Here again, so as I lower the temperature, high density, which are 5-coordinate and 3-coordinate, those from border coordinate I know which water molecule has how much volume, that rapidly decreases, and the low density molecules increases, and so fragmentation of high density clusters below 220 Kelvin is one of the reasons for this anomaly that we are talking. And there again, the number of, what we find that when you go into that, the number of defects scales like entropy. Number of defects decreases very rapidly near 220 Kelvin or so. So there is almost an exponential, explosive growth when you go above 220 Kelvin. So decrease of hydrogen bond defects in the hydrogen clusters is partly responsible, and then it is the another measure of heterogeneity, which is the chi-4 local density heterogeneity. The dynamics becomes much more heterogeneous, but is again I cannot go into that too much now. Going back now, the fraction. I was telling there are two kinds of water molecules, 3-coordinate water molecules. One water molecule, here the 3-coordinate, we call it O1H2. It is only one hydrogen bond binds oxygen, and both the hydrogens are hydrogen bonded. And this O2H1, these two oxygen can form two hydrogen bonds. It has formed both the two hydrogen bonds, but it has formed only one hydrogen bond through its hydrogen. So you have the asymmetry in water molecule hydrogen bond. It is something what one of my colleague, Professor Hegre, told me long time ago. He was doing spectroscopically. He came and told me, Biman, that the water molecules have two kinds of hydrogen bond. Those days I was very much in equilibrium statback oriented. I said, no, there cannot be. What happened in ordinary water, fluctuations are so fast, this difference gets wiped out. But in a low density, this really becomes very, very important, as I'll show. This is one of the reasons of this story. Beautiful story actually that is here. Other is 5-coordinate water molecule. These are the defects. These are the defects which you show how the defects are decreasing here. And here, oxygen forms 3 hydrogen bonds. And both the two hydrogens of the water molecules are hydrogen bonded. Now the O2H1, which is this guy, which is oxygen is doubly hydrogen bonded, but only one of these things, that guy decreases really sharply. This is the guy which follows much of the transfiguration or structural transformation. That particular thing, that one species, that this guy and this guy seems to be playing really, if you consider devil's advocate, much of the dynamics. I'll show you more picture of that going through this thing. 5-coordinated and this guy and O1H2, they are following very similar. Actually, they transform into each other, and their number is almost conserved. So density of states of defects, you can study how many, then you go and tell the defects, and you can look at the defects, do a vibrational coordinate analysis, and you can find out one beautiful answer of that. You can find the O2H1, the particular defect which plays the dynamically driving force, that has a very large density, vibrational density of states in this region, and that has an anomalously large high frequency imaginary modes. When you do an analysis, tentatively, you can get a suggestion from the vibrational density of states. When vibrational density becomes, the density of state, density becomes negative. That has physically the more robust meaning, but it has a very suggestive, means that has a short lifetime. Okay. And this is a very elegant analysis called instantaneous normal modes that has been developed late 1990s and 2000, debated, but it is not the thing which can prove anything, but it suggests that something very interesting happening along this particular hydrogen bond, which is O2H1, this guy, which is this guy. This is the guy, which is the active species. Okay. Then you look into the movie, again I don't have the movie, but you see this guy which is twice hydrogen bonded to oxygen, but only one of the hydrogen, that is the unstable species. And one finds at a very low density, like in 150 Kelvin, this guy triggers the excitations or hydrogen bond rearrangement. And at the hydrogen bond rearrangement takes place, it rotates and it translates by large amplitude. So this defect is the one that plays. And then you look at the displacement when such an event happened. Water molecule undergoes large displacement and large orientation. This particular defect. Okay, I don't think I'll be able to go a little fast, but not too much. So now we have put together a story that what are the anomalous properties of water over a large time and length scale, large temperature and density length scale, that what is happening, that there is a multiple dynamical transitions. There is the HDL LDL transitions around 220 Kelvin, where this LDL forms, low density liquid forms, which goes into become an amorphous ice, a little bit of that. And this is a very low glass transition temperature of water, which is more or less accepted, coming from the glass side, not from the liquid side. Glass side, you know for sure that glass transition is 136 Kelvin. Okay, not two-thirds. So water completely different. We have from Concord was saying of the protein folding, but water has this enormous amount of fascinating and secret properties. So little bit of water glass transition now. If you plot again all the universal characteristics, all the glass transitions of the liquids, this is some magnesium, there are many proper yttrium, I think these kind of things also came because of the superconductivity and other things. Okay. Now if I plot the entropy as a temperature, entropy minus entropy of the ice, then or entropy of the crystal here, because this is not ice crystal, then this is a very slowly varying thing. Or you can take it out everywhere. So this is your reference. This is melting. So at that point the latent heat, entropy difference is the latent heat. Now as you lower the temperature, this curves like that. It's beautiful. Really, entropy of supercooled liquid decreases much faster than that of the ice or crystal. And that is the reason why, the reason is that specific heat of a liquid is larger than that of a crystal. If you extrapolate it, usually it goes to glass somewhere. Here, as it's shown, it goes to glass transition. But if I extrapolate where below the glass transition, with the same curvature, it becomes, entropy becomes same as that of the crystal. It cannot go below that. But if with the point, it calls the Couchman temperature. It is where entropy of extrapolated liquid branch become that of the crystal, cannot be below that. I cannot have an entropy of a liquid less than that of a crystal. This is the end point, that's called Couchman temperature. Now what is the Couchman temperature of water? Nobody knows. Okay? But I will now for the first time give an estimate. So this is a glass transition scenario, and this is the angel plot, how glass transitions anomalous, non-Arrhenius behavior. This is how temperature is decreasing. And this is relaxation time of viscosity. It rapidly increases here. This is Arrhenius behavior. This is a non-Arrhenius behavior. At the extreme, it is called fragile liquid. Here, it is called strong liquid. And this is specific heat behavior. If you want, we will have these slides will be available in the video. Okay. Again, the glass transition is this situation. Okay. This is how universally all the liquids behave. This is how it becomes glass, but if I entropy, if I continue and extrapolate it, it will become same of that of the crystal, and that is the temperature, which is kind of end point, a limiting temperature called Couchman temperature. It was done by famous physical chemist Walter Couchman, who has done also hydrophobicity and many other things. Now comes again to theoretical calculation. There is a huge quantum effect in water which we didn't suddenly anticipate. Huge quantum effect in terms, this is the quantum specific heat and this is correct specific heat. These are agrees exactly with the experiment, and this is the specific heat of quantum corrected ice, which again exactly agrees with the experiment. This is known experimentally, fairly accurately, because if you calculate the specific heat of ice, and here it is again agrees experimentally. So there is a huge quantum effect. That quantum effect comes because that of the again water characteristics, hydrogen bond network. It has the libration at, you know, the librations at 600 centimeter inverse, one is 200 centimeter, and this rattling motion around 50 centimeter inverse. When you go to lower temperature, 200 centimeter inverse behaves like a quantum mode. 600 of course behaves like a quantum mode. So this extra density of states, which intermolecular vibrational density of states, because hydrogen bonding, they play a very important role, and you must treat them quantum mechanically. You treat them classically, you get classically, you go to Dulong-Petit's law. You go to Dulong-Petit's law, but you do not get the real picture. So quantum effects are huge, and as a result of that, the heavy water behaves very differently from the D2O behaves very differently from ordinary water. They are really fascinating properties, and I don't have time to go through that. Okay, I go back to entropy now. Again, this entropy is calculated from quantum corrected specific heat. I did not spend any time on this before, let me spend a little time on that. So we integrate. Remember, if I integrate Cp by divided by temperature Cp by T dt, I get the entropy. Cp I get enthalpy. And now I divided them. This is the total entropy, this is the configurational entropy, and this is the vibrational entropy. Look at that, not only configurational part, which I already showed you from configuration specific heat and configuration, that how quickly it moves to lower frequency. As it moves to lower frequency, it just goes out of the spectrum. Amplitude decreases, I already showed you that. And that is the configuration part. But look at that, vibration is much more than configuration. Thermodynamics of cold water around 250 Kelvin, which you face when you go to Manali, you will have 250. Many times this, that means the thermodynamics of low temperature water is determined by its vibrational modes, intermolecular vibrational modes. We never expected that, and that because of quantum effects. The quantum effects were not there, the vibrational effects were not there. Now is there propagation. Now, what happens to the amorphous ice that I form? This is the difference between amorphous ice and real ice, the ice that you form in your refrigerator. What I have plotted here, orientation, theta is an angle of one tetrahedral with another tetrahedral with another tetrahedral. And this is the distance. In ice, you see how correlated they are. The peaks are in definite crystalline hexagonal lattice positions. Amorphous ice, which is at 100 or 120 Kelvin, look at, there is no propagation. Their densities are fairly close to each other. But amorphous ice, no propagation of orientation correlation. And now your frequency dependent specificity. Again you see the huge importance of low frequency modes in the things. Now I define, now since I have a specific heat which is so, my low frequency part is so separated from high density part, I can define a frequency dependent entropy by Fourier decomposing this. And sure enough, my vibrational entropy is very distinct from my configurational entropy. And configurational entropy I want to define why? Because I have a time scale. So this is those configurations which are available only at this time. So now you have a thermodynamic property which is time dependent. People have defined before, because entropy is a dynamical quantity. I have a book, Water. There is an entropy of water chapter that will tell you how to think about entropy. Entropy is a dynamical quantity. You see, enthalpy is not a dynamical quantity. You can go and calculate the enthalpy. Entropy, no, because entropy is a collection of, remember Boltzmann, entropy Kb ln W or K ln omega. But how do you know it has omega? It has to explode configurations. Therefore, only you know its entropy. So entropy is a dynamical quantity. It's a very important concept. Entropy is a dynamical quantity, not enthalpy. Okay. that is the reason we can define a frequency independent entropy very rigorously for the first time in the world. Okay, so that kind of tells you the story that I wanted to tell. This is a beautiful picture here that how different amorphous ice is. So the basic picture that one is generated, this I glossed over. This picture is that there is a constant called Lindemann constant, which is a mean square displacement. That means you go to a particle, gets its average position, things are very slow, you can define average position, and then it oscillates, and you find out how much is the displacement. When a solid melts, that displacement goes very quickly, and when it becomes 10% of the cell length, that's where it melts. That's called Lindemann constant or Lindemann ratio. It's a phenomenology which is obeyed by almost all solids. It's universal characteristics. Chemists are not used to universality, but physicists refuse to talk of details. They will talk of universality. Okay. Now, universal is far more interesting than the details. It's far more interesting than doing a quantum calculation up to second decimal place. These are really big problems that I am talking here today. Okay. So, now Lindemann constant undergoes, and here it shows the Lindemann constant is this side, how Lindemann constant is growing. But the growth of Lindemann constant exactly scales with the entropy. And so this is the entropy again, entropy of ice, blue, then entropy of the supercooled liquid or glass. Is glass here, behaves very much like an ice. But then around 136 Kelvin it starts deviating. This multiple transfiguration that I am saying, then it goes, and one big one that goes on to become the liquid.